Good evening. Welcome to the 150th episode of MCQ class for the doctors preparing for the postgraduate examinations. Uh, this special episode is scheduled and we are celebrating the 150th episode this time. We have conducted 150 episodes of these classes during the last 10 years. And this time we received special request from Anuradhapura Medical Association to conduct this kind of class. In the meantime, we were also planning to conduct this class and we combined together. And so now we are going to start. So there are few things which I have already shared in the WhatsApp groups also. So since there were more than more than 1,000 registrations, we thought of uh, uh, we thought of getting a Zoom facility related to that, and we got to, if the participants are 1,000, we can only conduct a webinar. So we are doing this session as a webinar. Because of that, unlike a routine Zoom session, you will not be able to put your questions. So that's why we have we created two WhatsApp accounts. So you can post any questions that you have through the WhatsApp group, right? So our team, they are ready to help you with regards to anything that you have, because in the webinar, so I can see about how many participants, Emma? Now, yeah, so now nearly 500 participants are there with the Zoom, and nearly 100 participants are there with the YouTube. So we have shared the YouTube link as well. So you can leisurely later go through the YouTube video as well. Okay. So special message with regards to Anuradhapura Medical Association, because so we are doing this statistic class. So Anuradhapura Medical Association, so they have been doing these postgraduate preparation classes during the last 2 years. I think they have conducted nearly 50 those classes. So we will share the Facebook group. So please follow the Facebook group of Anuradhapura Medical Association. So you will see this kind of several classes with regards to radiology, medicine, surgery, for the several aspects. Okay. I think I have mentioned everything that you need. One word about this session. So I have already shared the resource material. So those who have newly joined to the WhatsApp group, we will share the resource material again, which contain 15 MCQs, right? So the whole discussion will be based on these 15 MCQs. Okay. So let's start. So I hope you can see my screen as well, right? So and I hope you can hear me. Right. So we'll start this one. So time to time, and so since there are 1,000 registrations, we will not be able to accommodate all these questions, right? So because of that, we have prepared special short notes for your reference. We will share time to time through the WhatsApp group, so you can refer leisurely. And before starting, I wish you all the best, and let's start this one. Right. Okay, I hope you can hear me, right? Right. Right. So I will give you about 1 minute. Just so I know some of you have already gone through the MCQ, some of you may not. Because of that, take 1 minute and go through the MCQ and try to understand something. Okay, now focus to the video, not to the video, but to the screen, to the MCQ. A study was conducted to assess the relationship between age and physical activity level among university students. Age was recorded in completed years, while physical activity level was categorized as low, moderate, and high. Which of the following statements describe a key consideration in this study? Even though it looks like true false, there's one answer. So which of the following statements? Yes. So this is a single based answer type question, right? So in this kind of question, you need to understand first. Right. So I will write here. I hope you can see what I'm writing, right? Okay. So there are two variables here. So one is age. So age is recorded as years like this, 28, 29, 30, like this. Okay. And the other variable is physical activity, which was recorded as low, moderate, or high. So the first one might having low activity, the other one also low, moderate, like this. So the two variables, right? So first understand the nature of this one. Then I will explain the basic things that you need to know with regards to this one before finalizing the answer. So variability or the variables are the key reason behind this subject called statistics. Uh, right. I hope you can see the screen. Right. Right. So variables, right? So variables are the things that change the quality or quantity from one observation to other. So variables basically can categorize variables as qualitative variables and quantitative variables. And special categorization is there, which is the essential thing in statistics, that is discrete and continuous, right? Discrete are the fixed numbers, fixed numbers. For example, the number of hospital days, number of days of the hospital stay. For example, the days can be recorded as 3, 4, 5. Number of students in classes, 34, 35. Basically, there are no decimals here. But when it comes to continuous, in the given interval, any number is possible, which are the things like height, weight, those are known as continuous variables. One other thing, not always true, but in general, these discrete variables tend to follow some sort of skewed distributions, while those continuous variables will follow normal distributions. But this is something not always true, right? So you need to understand these things. The other thing is, There are 4 scales that you need to know. Those are known as nominal, ordinal, interval, and ratio. Nominals are the variables where we measure it not as quantity. For example, so we can measure the colors. So colors, we are measuring colors like blue, green, like that. So we cannot say like blue is 2 times of green, something like that. There's no quantitative difference between these variables. Ordinal, we have little bit of quantity, but it's also basically, so we know, for example, CKD stage. There are 5 stages, CKD 1, stage 2, and until stage 5, right? So there are 5 stages. We know that 2 is severe than 1, 3 is severe than 2, but we cannot quantify. There's no quantitative difference like 2 is 2 times of 1, something like that. So ordinal is such variable. Interval and ratio are basically continuous variables, and one difference that you need to know is in interval variables we have a 0 which is not an absolute 0. One of the best examples is temperature. Temperature in Celsius. What do you mean by Celsius 0? What do you mean by Celsius 0? Celsius 0 means it's not absence of temperature, it's a temperature. And this ratio variable, it's ratio, it has to be ratio. Ratio variables, they have 0, which is an absolute 0. Examples, height, weight. Height 0 means no height, weight 0 means no weight. Simple as. If you understand these things, that's it. Let's move to the answers. So we'll discuss. Okay. The question, now as I mentioned, age, the 2 variables are age and physical activity. Now we know that age is a continuous variable, while if completed years, this has to be other than continuous, it's a discrete variable because it's measured in completed years. So no decimals. So this is a discrete variable, while the other one, the physical activity level, is a ordinal variable. Let's go to the answer. So we know that this is correct. The first one is marked. We'll go starting from B. Physical activity level is an interval variable. No, the physical activity is not an interval, it's an ordinal variable. Age must be categorized before statistical analysis. It's wrong. So this is also wrong. So this is wrong because it's ideal to analyze age without categorizing, but if you really need, based on your objectives, you can categorize also. But as this is must, there's nothing like that. We cannot say that age must be categorized. Because of that, it's false. Physical activity level. The physical activity level is a continuous variable. Wrong. Age becomes qualitative because it is recorded in years. Now, as it is recorded in complete years, it's not a continuous. Now it's a discrete variable. And the answer is first one. Age is quantitative variable measured on a ratio scale. That is the answer. So the basic idea is you should be able, so you should have some understanding about variables. So we have prepared a special note if you need to refer more. So we will share the our short note in the WhatsApp groups. We will put that short note into all the WhatsApp groups. Please share that particular short note. In the meantime, we will share some of the YouTube links as well, where I explain most of this stuff in detail than in MCQ. So then the knowledge with regards to this one must be completed. Okay, let's move on to the second MCQ. So okay, so I know that some of you have just joined, and because of that, so I will give you just 1 minute. Please go through the MCQ and try to understand. Question number 2. Okay. Okay, I hope you can hear me, right? Okay, question number 2. A researcher analyzed monthly treatment costs of patients with chronic kidney disease and uh, found the distribution to be positively skewed due to a few patients with very high expenses. Which of the following statements best describes a key consideration regarding this distribution? There are few things that you need to know, right? So there are few things that you need to know. I will explain those. The first one, right? So any variable, if we take the frequency distribution, that is, we call it as a probability distribution, those probability distributions have different shapes. The common shape that we know is the normal distribution. I hope what I am drawing, right? Normal distribution. In the normal distribution, you need to know the main property is mean, median, and mode are at the center. Mean, median, mode are at the center. And there are skewed distributions. There are several types of skewness, but we need to know two main skewness. One is negatively skewed distribution, so where the tail is towards the negative side, negatively skewed or left skewed distributions. Where the mean, median, mode will be, the mode will be at top. And the median will be at the center. And the mean is here. If you cannot remember those, I know some of you cannot remember these things. Your mean is the madhyanya or average value, the median is the middle value, and the mode is something called mathe. Right? I'm sorry, I don't know what are the names in Tamil. Okay. So this way. So what happens, mean is shifted towards the left side or the negative side in left skewed distributions. The other thing is right skewed distributions, where the mean is shifted towards right side, median is at the center, and the mode is at the top. So you need to know a few things. Those are, right, in normal distribution, to say as a measure of summary measure, if we are talking about the central tendency measures, we are going with mean. But median, mode are almost same to the mean. But when it comes to negatively skewed and positively skewed distributions, you need to know the median is always at the center, despite the shape of the original distribution. Despite the shape of the original distribution, the median is at the center. Because of that, median is the best measure of central tendency in a skewed distribution. That is something that you need to know. So up to now, we discussed the measure of central tendency. Measure of central tendency. Those are mean, median, and mode, right? And you need to know now. For example, now there can be three normal distributions. I will give you one example. So that is, okay, this is a distribution of marks of three different distributions, right? So this is distribution A, class A, where the average is okay, 80 marks, right? And this is class B, where the average is again 80. This is class B, but different shape. Then this is class C. Again, the average is 80, but it has a different shape, right? So even though the mean is same, these are three different distributions. That indicates not only the central tendency, but also we need to measure the spread of values, or we call this as dispersion. Dispersion or the spread of values. Right? So there are 5 things that you need to know. There are several measures of dispersion, and you need to know them. Right. Range. What is range? Range is the simplest measure. The difference between highest value and the lowest value. We can say this distribution spread from 90 to 100, 90 to 200. Like that, we can have some idea in addition to the measure of central tendency. But the problem here is range is sensitive to the outliers. Sensitive to the outliers. This is sensitive to the outliers. Why? So there can be, now assume that we are asking what is the distribution of height in Sri Lankan male. So we can say it's 5 feet to 6.5 or something like that. So assume that we have a person whose height is 8 feet. Then we might explain it as our range is from 5 feet to 8 feet, which is not true because that is the only person who's having height of 8 feet. So that is an outlier. So range is sensitive to outlier. Because of that, there's another measure that is IQR, or interquartile range. Interquartile range. If you can remember small h mathematics, we learned this, and in Sinhala medium, so we call this as antas chatushtaka parasya, interquartile range. The whole distribution is divided into 100 different parts, and the center is the median. We call this median as Q2, and the 25th position is the Q1, and 75th position is Q3, and interquartile range is the interquartile range is Q3 minus Q1. we can have some understanding about these one. And I need to explain, but the problem of these two, range is sensitive to the outliers, interquartile range is not sensitive to the outliers. It is not sensitive to the outliers, but we are talking about whole distribution using only two values. Using only two values, we are describing about the whole distribution. Because of that, we need a measure of dispersion, which um, based on all the values in the distribution. Because of that, we have introduced something called variance. I'm not going to discuss all these things. And the standard deviation, which is the square root of variance. And nice practice, standard deviation is there in the x-axis of the distribution. Right, standard deviation 1 and 2. So based on that, we can talk about this one. And there's another one, that is coefficient of variation. Coefficient of variation, right? So that is SD divided by mean multiplied by 100. Right? That means SD low. Low SD means distribution is not that dispersed like this. But if the SD is high, it will be a dispersed like this. So I will discuss a little bit more about coefficient of variation with the MCQ. Okay, so let's go to the MCQ again. Right. Right. So the mean, median, and mode are approximately equal. Now it says that, so we are talking about the expenses of chronic kidney disease patients, which is skewed to right or positively skewed because of positive outliers. Some patients are spending more because of that the distribution is positively skewed. So the first state that the mean, median, mode are approximately equal, which is wrong. And the second one is the interquartile range is more affected by extreme values than the range I mentioned. Range is affected by the outliers, extreme values, or but interquartile range is not, which is wrong. The third one, the coefficient of variation is calculated by dividing the variance by the mean. No, I said it's divided by S. Standard deviation divided by mean, so it is wrong. The mean is likely to be pulled towards higher values. Yes, that is the answer. Because of the positive, the mean is shifted towards the highest side, towards the higher side. The next one, the standard deviation represents the middle value of the data set. Now, the middle value represented by the median. Because of that, it's strong. Okay, let's go to the question number 3. So again, I mentioned now, I think nearly 800 are joining with us. Some are through the YouTube, some are through the Zoom. So those who have newly joined, I need to mention we have already shared the MCQ file. We will share it again if there's anybody who has joined recently. So we will share that one also. And if you have any questions, please put in the WhatsApp group. So we will try to accommodate all these questions. And also we will share the notes and the resource videos through the WhatsApp. And now I will give you just 1 minute to go through this question. In the meantime, we will share the Anuradhapura Medical Association Facebook page link, because they are conducting so many postgraduate classes, not only statistics, related to almost all the subdisciplines. Please follow the page so you can participate those classes online. Okay. Okay, question number 3. A researcher wants to study why some patients discontinue tuberculosis treatment despite free medication availability. The study aims to explore sensitive personal experiences, group attitudes, and also collect standardized socio-demographic information from the patients. Which of the following is the most appropriate combination of data collection techniques? So when it comes to data collection, we need to extract several things. The common thing that we use is questionnaire. Either a self-administered questionnaire or interviewer-administered questionnaire. Interviewer-administered question. But the problem with this, and in addition to there are things like event calendars. We can mark the sequence of events, how the serum creatinine has been changing over the time, how the symptoms are changing over the time, so something like that. So event calendars. But with these things, the problem here is, we can extract the things we know. If the researcher knows something, we can include that as a question. But if we don't know something, right? So we need to extract this data by some other means. So qualitative studies focus in that aspect. We need to understand the deep thinking. So because of that, there's something called qualitative studies. In qualitative studies, basically we are extracting that the researcher doesn't know, but the people might know. One of the best example in our life is, now everywhere in the world, we know that esophageal cancer is male predominance. Males more than female. One of the consultants from Wu province said that there's a female predominance. When we are looking at the statistics, that is true, but we don't know the reason. So we need to find out whether there's something in it, but we cannot extract this data using a questionnaire or event calendar. In that case, there are several techniques which are used, such as in-depth interviews. I can remember this question came in one of the GINOPS selection exam. In-depth interviews, focus group discussions, participant observation. One of my student group did a research, so they need to understand what are they need to understand the thinking process of the OPD patients in the hospital queue. What they did was they changed their address, not as to medical students, but as the general public. They went to the OPD and they did some participant observation and diary interviews. So many methods. These are qualitative data extraction techniques. Let's go to the question. Now, this researcher needs to understand why patients discontinue tuberculosis treatment despite free medication availability. The study aims to explore the most important thing is sensitive personal experiences. Most probably personal experience we will not be able to gain through a questionnaire. In that case, we might need something like in-depth interviews. And for the group attitudes, we can interview the groups, things like focus group discussions. and also collect standardized socio-demographic information. Definitely, we need self-administered or interview-administered questionnaire. Okay, the answer one, self-administered questionnaire through structured observation. So we can do that, but the laboratory investigation are not relevant. So the answer is wrong. In-depth interviews correct, focus group discussions correct, interview administered correct, and most probably this must be the answer. And event calendars, so there's no need of event calendars here. Structured observation, self-administered questionnaire, biochemical measurement because of the biochemical measurement, that is wrong. And record interview, that is possible. Laboratory investigations again, which is not needed here, and interview administered questionnaire is correct. So the best answer is B. Okay, let's go to the question number 3. Okay, this is the format. I will give you another 1 minute for those who have just joined, and just go through this one. Okay, I hope you can hear me. Right. The question number 4. A laboratory has 20 rats in a cage for an animal experiment, and 5 rats need to be selected as the sample, as a random sample. So we need 5 rats out of 20 rats. The researcher inserts a trap through a small hole in the cage and captures 1 rat at a time without looking inside the cage. Which of the following best describes this sampling method? So here, there are several books written on sampling techniques. Because of that, I will share our resource material with you. So we will share the resource material of sampling techniques. Please go through that. But I will discuss briefly what are the things related here. Okay. So there are two methods of sampling. You can see those are probability sampling and non-probability sampling. Probability sampling, we can obtain a representative sample, while in non-probability sampling, we don't know, or the extracted sample, we don't know whether it's random or not, whether it's representative or not. Generally, we don't take a random sample from non-probability sampling. There are 5 random sampling techniques. Those are simple random sampling, systematic sampling, stratified sampling, cluster sampling, multi-stage sampling. Right? And when it comes to non-probability sampling, there are several hundreds of sampling techniques. Even probability sampling also, there are more than this, but we are focusing on 5 main these techniques, right? So I have included this picture in the resource material as well. You can see in simple random sampling, we are taking from the whole population. Generally, this is good for small populations. Each and everyone in the sample has equal chance of selecting. When it comes to stratified random sampling, right? If there are So it is good for heterogeneous populations. There are Sinhalese, Muslims, and Tamils in the population. We are taking the hemoglobin level, and we assume that there's a difference between hemoglobin level between ethnicities. Then we might need to take a sample from representing Tamils, Muslims, and Sinhalese. So in that case, stratified random sampling. Systematic sampling, we are taking every K person. So we should have the list and assume that we have 500 patients and we need a sample of 50. So we divide 500 by 50, that is 10, and we are going to take every 10%. There are pros and cons in each and every techniques, which I have discussed in the resource material. Please refer the resource material. And basically, this cluster and multi-stage sampling are for the large populations. So assume that there are 20 MOH areas in a district, right? So if almost all MOH areas share similar characteristics, right? We might extract samples from here. Assuming then that all are same, we extract one sample, right? Multi-stage sampling is good for the large-scale island-wide surveys, right? So we go by like provinces, districts, like steps. Okay, so that is the basic idea about this thing. So please refer the resource material which I have shared just now in the WhatsApp group. Those who couldn't join the original WhatsApp group, please follow the link and join the new WhatsApp group, because the parts generally we can take only 1,025 groups. I have created the second WhatsApp group as well. So all the links displayed everywhere is regarding the second WhatsApp group right now. This question is an interesting question. So now there are 20 rats in a box, in a cage. There's a small hole, and this particular research is trying to insert a trap through this hole and take 5 rats from here. What are the problems? Sample is biased because the researcher may still see inside the cage. That is true, but the problem is this is still see. So researcher may not see. Because of that, if there's no other very good answers, we can consider this as true. But still there's a probability of looking at, but here it says the researcher is taking without looking at the cage. The next one is, it is a simple random sample because each rat has equal chance being captured. That is also true. These are the real kind of single best answers where we get all the 5 answers are correct. You have to find out the best answer. That's why they are known as single best answers. Best answers are there, but there's a single best answer. Okay, correct. This is also correct. But here also there's a problem. I will explain that one. The next one, sample is biased because weaker rats are captured. Generally, what happens in animal experiment is, if you put this trap inside, what will happen is the energetic rats will go away while the weaker rats are captured to this one. So this is also true. But if there's a high probability of capturing weaker rats, that is not simple random sampling. Because of that, this is wrong. And the fourth one, this is systematic sampling. No, it's not systematic sample. We are not taking every second or something like that. And the method is unsuitable because some rats may die due to the trap. So it may be true, but it's not relevant here. So the best answer is C, but I need to mention A, B, C are true, but as there's a probability of weaker rats to be captured, so this is also wrong. And so we cannot exactly say whether the researcher will look inside the cage. Okay, so question 4 is done, but there's no time to discuss all the aspects of sampling. Because of that, I have shared the research, the short note regarding this one. Okay. Question number 5. Okay, I will give another 1 minute. Please go through this one and we will discuss them. Okay, before talking about the question, I hope you can hear me. I hope you can hear me, right? Can you hear me? Okay. I need to discuss little bit of theory here. Okay, give me 1 second, right? Assume that this is a population distribution. Population distribution of simple example. We take a simple example, birth weight. Population of birth weight, where the mean birth weight is 3 kilograms. And standard deviation might be, okay, 500 grams. So it's 3.5 here. SD is 500 grams. Right? It's normal distributed sample. This is population distribution. This is population distribution. We can take multiple samples from here. We can take multiple samples from here. We will take n number of samples. This is small samples, right? So this is sample 1, okay, sample A, and sample B, sample C, and like that we will take n number of samples. I mean, not n number. We will say sample 1, sample 2, sample 3, and a large number of samples, sample n. And we'll calculate the mean of these samples. The population is 3, population mean is 3, and we will calculate. Okay, x bar, we will name x bar 1, x bar 2, x bar 3, and n sample x bar n. Right? If these samples are random and representative samples, if they are random and representative samples, all these samples must be almost similar to 3. If we take another graph and we plot 3 here, and we can plot these x bar, n number of x bars here, then you will see most of the x bars will be more or less closer to 3, while lesser number of x bars are not closer to 3. Because of that, at the end, this sampling, this is what is called, this distribution consists with sample means, which is known as sampling distribution. The standard deviation of the sampling distribution is known as standard error. Practically, we don't take these kind of multiple samples, but we take just one sample, which is random, representative, and inadequate size, and we calculate the standard deviation of that sample, and based on that, we calculate standard error using this specific formula called standard deviation divided by the square root of n. One thing about this standard deviation, ideally this has to be population standard deviation. Keep in mind, this has to be population standard deviation, but practically we take the standard deviation of random and representative sample, right? This is how we calculate. In reverse, the reverse thing is, now if we know this standard error, right, standard error, we can have some idea about the sampling distribution. And if we know the sampling distribution, we can say those sampling this sample means outside are slightly different from the population means. Slightly different from the population means, right? But these are almost similar to the population mean. Because of that, in theory, I have to explain a big theory here. If a sample mean consists with sample mean is plotted in the area beyond the predetermined cutoff value. Beyond the predetermined cutoff value, generally that is called 0.05 or 5% region. We call this, if something is in this region, in the sampling distribution, but not in the population distribution, right? Not in the population distribution. If something is there, we call it as statistically significant. And based on this standard error, we calculate something called 95% confidence interval. Then how are we going to interpret 95% confidence interval? Generally, I think it has to be the statistic plus or minus mean plus or minus statistic, either T or something, statistic into standard error. But generally, if you can remember, this is mean plus or minus 1.96 or 2 standard errors, because that is the 95%. That is the 95%, right? Okay. Now here, then one thing about this one, how are we going to interpret the 95% confidence interval? Okay, the birth weight is 3 kilogram in the same example. The mean is 3 kilogram. Standard error, assume that it is 100. So the 95% confidence interval roughly is 3. That is mean plus or minus 1.96. Assume that it's 2 standard errors. That is standard errors 100. So the 95% confidence interval means 3 kilograms plus or minus 200 grams. That is 2,800 to 3,200. How are we interpret this one. This is very important. There are several ways of interpreting. We can explain all these things. So I will share those videos related to 95% confidence interval, sampling distribution, those things. You can go through them leisurely if you have time, and you can understand if you really need this, because some of the postgraduates, they need to understand all these things in depth, but some just for MCQ. Because of that, we will share that one, and we will share the resource note also prepared for the sampling distribution, p-value, and the 95% confidence interval. So go through that one. So the next important thing is, how are we going to interpret this one? General accepted way is, we can say now we don't know this population distribution, we know the sample one, and based on this, we can say we are 95% confident that the population mean should be in this range. That is how we interpret. We are 95% confident that the population mean is in this range. Right? Okay. So there are some different interpretations with regards to odds ratios and all. So I will explain then and there. Okay, let's go back to the question. Question number 5. After reviewing the medical records of 100 young adults, age 18 to 45 years, who were admitted with acute myocardial infarction over the past 3 years, a cardiologist calculated that the mean troponin I level at the admission was 2.6. with standard deviation of 0.9. She wants to include statistical measure in her departmental audit report to estimate how precisely this sample mean reflect the average troponin level among all young MI patients treated at her hospital. Which of the following is most appropriate measure to include? Standard deviation is correct, but standard deviation is to describe about that particular distribution, either population or sample. So it's difficult to get some idea about the population using the sample values. Because of that, this is not the ideal answer. Sampling distribution is something, one of the best answers, but still sampling distribution is about all the ones, but we are interested about the population mean, and the standard error is the standard deviation of sampling distribution. Because of that, we can have understanding about the dispersion of this one, but the answer is confidence interval. Why? We are specifically give a range for the population mean or the population parameter. It can be the mean or something else, whatever it is, the population parameter. So we are using confidence interval to talk about populations based on the sample data. Range also can be used, but it's not the ideal answer. So the best answer in this SBA question is D. Okay, I hope you understand. If you have any questions, please put on the WhatsApp group. Let's move to the next question. Yes. So that is about p-value and type 1 error. I will explain those things. Please go through. I will give you 1 minute to go through the question. Then I will explain. Okay, I hope you can hear, right? So this is about the p-value and type 1 and type 2 error. When it comes to p-value, this is an interesting topic. P-value, but I'm not going to discuss everything. So we will share the note for the short note, and many of you are asking the other notes. At the moment, we are finalizing those notes, and I will share at the end of this one how are we going to share all the notes soon. But we will share all the notes that we have almost completed. We will share those notes with you, so without any problem. And with regards to p-value, right? P-value is the final point in statistical analysis. Based on the p-value, we say whether something is significant or not. Right? I hope you follow me. Right? The p-value is significant. Based on the p-value, we are talking about the statistical significance, whether something is significant or not. In general, we are going with 5% level. If the p-value is less than 0.05, we call it as statistically significant, and the p-value is more than 0.05, we call it as not significant. That means basically this 0.05 is not something universal cutoff. The researcher has to decide what is the cutoff level that we are going with. And there's an interesting thing that you need to understand with this one. Right? There can be p-values equal 0.04, where we come into conclusion that this is statistically significant. However, in the population, right? In the population, even though we come into conclusion as this is statistically significant, when it comes to population, it may not be significant. So we have made a mistake. That mistake wrongly come into conclusion that something is positive or something is significant. We call that as false positives, right? So we call this as type 1 error. Type 1 error. Type 1 error. Right? False positives, so wrongly conclude something as statistically significant, or mistakenly we reject the null hypothesis. In this case, statistically significant means we reject null hypothesis, but population level it's not. So that is what is called type 1 error. How are we going to overcome this one? In order to overcome this type 1 error, the most probable thing is we have set this 0.05 mistakenly. If we need to overcome this one, we may select something like 0.01. We can shift the p-value, the cutoff value, to something small, because for this specific research, this may not be correct. This is the correct thing at the population level. So if our cutoff is 0.01, we may not come into conclusion as this is rejected because this 0.04 is more than 0.01. It's what is called type 1 error. The next one is assume that the P is 0.06, where we say that no significance, or we don't reject the null hypothesis. Null hypothesis is the opposite of hypothesis generally, right? Or negative form of the hypothesis, right? But in the population level, this is wrong. Population level, right? We might see that this is actually significant. So we have wrongly said something is not significant. We call this as type 2 error. We call this as type 2 error. Generally, to overcome type 2 error, this happens in almost all the time when our sample size is not adequate. Size is not adequate. If the sample size is not adequate, we might falsely say that something is not significant. In that case, to overcome type 2 error, right? We can increase the sample size. In summary, in order to overcome type 1 error, we have to change the significance level, while in order to overcome type 2 error, we can increase the sample size. Okay. Right. A clinical trial compares two cholesterol lowering drugs in 500 patients, 250 per group. The mean LDL reduction is 12 milligrams per deciliter greater with drug A than drug B, with p-value of 0.04. P-value 0.04 means at the 5% significance level, right? It is significant. That means with drug A is significantly reducing the cholesterol level. Yes, drug A is better and it is statistically significant. Right? The study was originally powered 80%, but only 70% of the planned sample size was enrolled. They couldn't achieve the full sample size. Full sample size is not achieved means that case there's a possibility of having type 2 error here, because we have not achieved the sample size. Which of the following statement is the most appropriate? Right, okay, let's go. But here, even though the sample size is not achieved, still the results is significant. That means this is something very important, right? Even though assuming that our methodology and data collection, everything, analysis, everything is correct. Assuming everything is correct, even with the lower sample size, we received something significant means there's no type 2 error at all. So, but here the point is, if any question, if they are talking about the sample size is less, that indicates type 2 error. Then look at the p-value, which is significant, then type 2 error is not possible. Here the p-value represents, answer A, the p-value represents the probability that the null hypothesis is true. This is partially correct statement, and many places this is given as the definition for the p-value, which is wrong. Type 1 error would occur. Yes, type 1 error is possible here if we conclude drug A is superior when no true difference exists. Yes, that is correct. Type 1, this may be type 1 error. This is correct statement. But the problem here is even now significance is achieved with lower sample size, right? And there's no clue about type 1 error, so we don't know. And the next one is p-value is a conditional probability representing the probability of observing 12 milligrams per deciliter or more extreme difference given that the null hypothesis is true. Yes, so that is the answer. This is the original definition for the p-value. Probability of observing something. So in our sampling distribution, if you can see in our sampling distribution, this is a sampling distribution. So dark color areas are beyond the cutoff value. So cutoff value. So the p-value is probability of observing here or extreme area, right? Probability of observing extreme area, right? So this is the original definition. And I need to give you some specific clue here, but nowadays this is not happening. The thing is now in these kind of questions, when the examiners are preparing the question paper in the scrutiny board, they are discussing. Many people are arguing against. So now A must be correct, B must be correct. So to make that the some to make a particular stem as correct, but they are trying some extra efforts. In that case, if you see the MCQs about 10 years ago, most of the time, the best answer is the answer with the longest step. The reason is during the scrutiny board, the people are trying to make it more correct, right? Later they found statistically, so that is something there. So nowadays, if that particular chief examiner has received this specific training on making MCQs, how to make MCQs, if that particular examiner has this training, they are trying to make it shorter. Even when I prepare MCQs, what I do is, if I feel that the correct answer is too lengthy, I try to make it shorter. Okay, so this is the answer. Next one, the study may be at increased risk of type 2 error. That is very correct. But but the problem is with low sample size, we have achieved something significant. Okay, so it's wrong. Statistical significance allows confirm that this is the most important thing. Even though you pass exam or fail the exam, statistical significance does not mean the true significance. So that is statistical significance. There may not be real clinical effect, even though that is statistically significant. So this is one of the most common stem in many of the MCQs. They are telling that statistical significant means clinically significant, which is wrong. And keep this clue in mind. Most probably, if one stem is like abnormally lengthier, most probably, if you do not have any clue, that might be the answer. Okay. Okay, let's go to the next question. It take 1 minute and do the question, and I will recall you. We will share the Anuradhapura Medical Association Facebook page. Please like the Facebook page, because they are doing like the preparation class for almost all the disciplines and including the sub disciplines also. So you can participate in those classes conducted by Anuradhapura Medical Association. So we will share the link. In the meantime, we will share the notes as well. Okay, I hope you went through the question, right? Right. So this is the most important question and the most commonly appearing question in the selection examinations, especially the selection examinations. Okay, and we will discuss the question number 7 and question number 8 together, right? So I mentioned you there are normal distributions and there are skewed distributions. If the distribution is normal, generally we select statistical tests known as parametric statistics. While for skewed distributions like this, we go with non-parametric statistical tests. Non-parametric statistical tests. So you need to know about parametric statistical tests as well as non-parametric metric statistical tests. Right. So we will discuss the question number 7 and question number 8 together. At the end of this session, you will be able to you will be able to say what is the best statistical test for any of the places. Okay. I hope you can hear me, right? So here we will discuss this. The scenario. Okay, scenario. And here the parametric tests and the non-parametric tests. Right. And I forgot to mention something important because I even get so many comments regarding now. Now today we are doing the 150th episode of this MCQ class. We did the 100th episode in the similar way. So many of them are watching the 100th episode video because we are discussing most of past papers up to 2022. So you can watch that video. We will share the 100th episode video, and even the many people who have joined this class also said that they came to know about these classes through the 100th episode. Okay, so we are going to discuss. Okay, in general, we need to compare a mean against a fixed value. Okay, a syrup, example, a syrup, the label says the syrup contains the sugar syrup contains 10 milligrams per deciliter. The sugar concentration is 10 milligrams per deciliter, right? But we are not sure. What are we going to do is we are going to take a sample of syrups and measure the sugar amount and calculate the average, and we calculate the average or the mean of mean sugar concentration of these syrups, and we compare against the fixed value in the label, that is maybe 10 milligrams per deciliter. In order to compare mean against a fixed value, if the distribution is normal, if the distribution is normal, the parametric test that we should use is one sample t-test. While if the distribution is not normal, we might be able to we may not be able to compare mean against a fixed value. In that case, we may be comparing median against a fixed value. But the non-parametric parallel scenario for compare a mean against a fixed value, that is sign test. So here it's one sample t test. Right. Another scenario, we need to know whether who is having more cholesterol, right? More cholesterol, lady doctor, female doctors or male doctors, right? So we have hypothesis whether the total cholesterol level is higher among males or females. So what we are doing is we need to calculate the mean. We need to take a sample and calculate the mean of males and against the mean cholesterol level of females. Here we have two samples, right? And we calculate the means and we compare the male means against female means, right? Male mean against female mean. Here, the test that we need to use is two sample t-test. Two sample t-test. The non-parametric alternative for the two sample t-test is Mann-Whitney U-test. Mann-Whitney U-test, right? And there's another scenario, right? We may need to compare not two mean, but means. Okay, mean cholesterol level among doctors versus mean for lawyers versus mean cholesterol level of farmers. Three groups for two or more means: mean of doctors, mean of farmers, and mean of lawyers. In that case, if these distributions are normal, then the parametric test is ANOVA. ANOVA. The non-parametric alternative for ANOVA is Kruskal-Wallis test. Kruskal-Wallis test. Right. Then another thing, we might need to compare, okay, whether there's a significant difference between the pre-pregnancy hemoglobin level and the post-pregnancy hemoglobin level. So we know that the mid-pregnancy has lower hemoglobin concentration, but somebody might be interested in knowing the mean hemoglobin concentration of pre-pregnancy versus mean post-pregnancy. Whether we are having the same concentration pre and post, right? Okay, so here we don't need multiple samples. Here we don't need multiple samples. We can measure the same sample in two occasions. Same sample, two occasions. Same sample, two occasions. The test is paired t-test. Paired t-test. If the distributions are not normal, we have to use non-parametric test. That is, there are several tests, but commonly used one is Wilcoxon sign rank test. And also, I have seen in one question, so for the Mann-Whitney test, there's another Wilcoxon test that is called Wilcoxon sign rank sum test. There's something called sum for the main. For Mann-Whitney, one alternative is Wilcoxon sign rank sum test. But here the sum word sum is not there. Wilcoxon sign rank test. Right. Another thing is we might need to know whether we are having high cholesterol level with blood sugar. Right? In that case, we have x-axis and y-axis. We plot sugar in x-axis while total cholesterol level in the y-axis. Right. So what we do is we plot these things. And we see the association. We will discuss with the final MCQ this one. To see this association, the test that we use is Pearson correlation test. Pearson correlation test. The non-parametric alternative is Spearman correlation. Right. The next is, without considering this non-parametric or parametric, this is considered as non-parametric test, but we need to know something about chi-square test. We need to know whether who are more sensitive, and assume that we have a scale. With the scale, we can categorize somebody is sensitive or not. No sensitive. And we have a hypothesis whether the male doctors are more sensitive or whether the female doctors are more sensitive. We take a sample of 100 male doctors and we might say the 45 are sensitive, while among the female doctors, we can say like 35 are sensitive. We can see whether there's a statistically significant difference between the proportion of male doctors versus female doctors. To compare proportions, the test that we need to use is chi-square test. There are more details about these tests. I will share the short note that I prepared. There's a table and there's a brief description. In this short note, I have not included any statistical terms, any specifically the statistical jargon is not there. So you can, as medical people, you will be able to understand them more easily. So please, have a look on this short note. Now we will share that short note as well. Okay. Right. This one, trial compares mean weight loss between two. This is very important thing, right? Now, weight loss, when you hear the word weight loss, you might feel that, right? So we have diet program A and diet program B. We have pre-values and post-values. We have pre-values and post-values. Right? Then when pre and post to compare, if we need to compare pre and post, the test is paired T. Here also we can compare pre and post using paired T. But actually what happens is, there is a difference here. What we are comparing is the two diet programs, not the pre and post values. We have difference. Okay, we have a difference here. Difference. Okay, so difference 1, difference 2, difference 3, like that. So we have this difference distribution, and here also we have the difference 1, difference 2, difference 3, like that. 3 and 4, 12. So we have another different distributions. So we need to compare those two. This is again like comparing the mean of males and mean of females. This is something like that. So here the pair T is wrong while we need to compare the two distributions, right? Okay, weight loss in kilograms, right? Two distribution. So, and here, and the other thing is when it comes to weight, they are in general, the weight will follow normal distributions, and this is a continuous variable, but not all the continuous variables will not follow normal distribution. Because of that, pair test is wrong, and chi-square test we compare proportions, that is wrong. Pearson correlation coefficient we are comparing x and y axis. Here we don't have, we have two variables. One is diet program, the other one is weight loss. So we cannot plot it there. So this is wrong. One way ANOVA, of course, we can use, but the problem is this is for two or more. We can use it for two even, two or more. An independent sample, independent two sample t-test is the answer because we are comparing two samples. The mean weight loss of the diet program A versus the average weight loss of the diet program B. The answer is independent two sample t-test, but there is this also correct because we can use two or for two or more means. But the paired t-test, the commonly mistake. So this is a common mistake that I have seen. Many people are putting this as the correct one by looking at this weight loss. So which is wrong. So the answer is independent two sample t-test, or we call this, another name for this is pooled t-test. Not full, it's pooled t-test. Pooled t-test. And the next one is the researcher wants to compare number of sugary drinks consumed per week between. So now you can see this is a discrete. We cannot have like 1.75 sugar drinks or something like that. Okay, between males and females. We have males, we have females, and we have a discrete count. We'll have a median count for males and the median count for the females. So this will not follow normal distribution. Most of the time, these will be skewed. As they are skewed, we have to select non-parametric statistical test. And since we have two samples, right, two samples to compare this median against this median, the best answer is Mann-Whitney U test. ANOVA is a parametric test. Z test is a parametric test. Z test, I have included that in the short note. Z test is almost like a t test, but t test is for small samples, while Z test is for large samples. Samples with when we know the population standard deviation. Welch t test is the correct answer. When we can use that one, we can use that one when the samples are not following the normal distribution, but the best answer is Mann-Whitney test because this is about parametric. An independent two sample t-test, we will not use this one because parametric. The best answer is Mann-Whitney test. Okay, I hope you understood something, and please make sure that you know these tests, right? And I think we have already shared the lecture note as well. Right, okay. I will give you another 1 minute. Please go to the question 9. I think in the meantime, we will take a short break, right, to refresh ourselves. Then we will restart, but still, I will let you know. Once our dinner is received, we will stop for the dinner. That means like a short break, and we will go ahead with the rest. But still, we have not received our dinner. Because of that, we will continue. And okay, please read the question number 9. Okay, many are, I hope you can hear, right? Okay, many are requesting to discuss about sensitivity, specificity, funnel plot. Okay, we will be discussing. Those are included, right? Okay. Let's now we have completed almost all the statistics parts. So we will move on to the research methodology part. So here the important thing is this is about the study designs, right? So first of all, I would like to let you know about the study designs, right? Study designs can be categorized as descriptive, and analytical. Right? There are several descriptive studies where we describe only. Those are case report, case series, cross-sectional studies, where we see the prevalence. What is the prevalence of diabetes? What is the prevalence of hypertension in the community, like that? And correlational studies, where we see the association between X and Y axis. This is summary, where we describe things. There's no much analysis there. But when it comes to analytical studies, there are three major types of studies that you need to discuss. Those are case control studies, cohort studies, and experimental studies or interventional studies. One important thing that you need to know is, right, except these experimental studies, all these studies, these are topics, right? All these studies, right? Case report, case series, cross-sectional, correlational, case control, and cohort. These are known as observational studies. While experimental studies are the only category of experimental studies, because there's another categorization known as observational and experimental, right? We will share this note as well with regards to study designs. We have prepared one note to explain the different study designs. And we will explain these things one by one, case control and cohort studies. First, we'll go with one of the example of case control study. Here the lung cancer. So you can please see this one. The same note is prepared. We will share the case control note as well and the cohort note as well. So we have lung cancer patients and no lung cancer patients. And one important thing is, like in case control study, in any case control or cohort study, we see the risk factors. When it comes to risk factors, there are exposures and outcomes. There are exposures and outcomes. But in case control studies, we go from outcome to exposure. We go from outcome to exposure, right? We go from outcome to exposure. And the important thing is, here from the beginning of the study, we do have patients and healthy individuals. And we go back and see whether they have exposed or not exposed. Healthy, we go back and see whether they have exposed or not exposed. Right? Here we have lung cancer patients, no lung cancer patients, smokers and non-smokers. Right? So out of 200 lung cancer patients, 120 have smoked, and out of 200 no lung cancer patients, only 60 have smoked. So the measure of association in case control study is odds ratio. How do we calculate odds ratio? We get the cross value, cross product, that is 120 multiplied by 140 divided by 80 multiplied by 60. The answer is 3.5. What do you mean by 3.5? 3.5 means 3.5 means there's 3.5 times risk of developing lung cancer among smoked compared to non-smokers. There's 3.5 times risk of getting lung cancer among smokers compared to non-smokers. That is the odds ratio meaning. The other thing is with the odds ratio, okay, the study conducted in Rwanda says that the 95% confidence interval, their odds ratio is 3.5. The 95% confidence interval is 0.5 to 4, while another study conducted in Uganda says the 95% confidence interval is 1.5 to 5. Okay, one thing. If this odds ratio is, if this odds ratio is 1, what do you mean by it? Odds ratio 1 means there's 1 times risk. That means risk is equal among between the smokers and non-smokers if the odds ratio is 1, right? So the 95% confidence interval says, even though in our study the odds ratio is 3.5, 95% confidence interval says the odds ratio in the population level, this can vary from 0.5 to 4. 0.5 means 0.5 times risk. That is a protective factor. If this confidence interval includes the value 1 or the null value 1, this result is not significant. If this 95% confidence interval does not include the null value 1, here it does not include the null value 1, this is significant. That is how we say the statistical significance. So initially we have to calculate the odds ratio, and you need to know the interpretation. There's 3.5 times risk, and you need to look at the 95% confidence interval. And if the 95% confidence interval includes the null value 1, that means 1 times risk, that result is not significant. You will understand more with the next slide, that is about cohort studies. Cohort studies, unlike the other thing. So first we get smokers or the exposed people and non-smoked people or the non-exposed people. And we follow up the patients and see how many of them are getting the disease plus, and how many of them are not getting the disease. How many of them are getting the disease and how many of them will not get the disease. Right? This one. The measure of association here is relative risk. How are we going to calculate the relative risk? We need to calculate the incidence among exposed, that is 90 out of 500 smokers have developed the disease. 90 out of 500 patients, and you need to divide that by 30 out of 500 patients developed the disease. Assume that it is lung cancer. The answer is 3. How are you going to interpret this one? There's 3 times risk of getting lung cancer among smokers compared to non-smokers. There's 3 times risk of getting smokers compared to non-smokers. And you need, and 95% confidence interval is also important here. 95% confidence interval says, okay. Right? Okay, there are 2 studies, the Rwanda study and Uganda study. The Rwanda study, their odds ratio relative risk is 2, and their 95% confidence interval is 0.5 to 7. then this interval includes the null value one, because of that this result is not significant. And in the Uganda study, they have a relatively low relative risk 1.6, but their 95% confidence interval is 1.2 to 1.9. That means 1.2 to 1.9. That means this interval does not include the null value one. Even though this has a low value, this is significant, right? So you need to know how to interpret the relative risk and interpret it in relation to 95% confidence interval. Okay, little more clear. And then about the experimental studies, right? Experimental studies, right? Nowadays, I have seen in many papers, they are asking about the experimental studies. The types of designs, randomization, the quasi-experimental studies, the advantages, limitations, effectiveness, biases, the phases of trials, the minimization of errors, right? This slide includes all these aspects, right? This slide includes all these aspects, right? But here there's no much mathematical things. Because of that, I'm not going to discuss, because this is another 3 days workshop to introduce the clinical experiments. Because of that, I have prepared 3 notes, which I will share right now. So you can leisurely go through the definition. What do you mean by per protocol analysis? What do you mean by allocation concealment? What do you mean by those things? And if you have any questions related to that, now we have 2 WhatsApp group. You can frequently communicate. Please post your questions with regard to experimental studies into the WhatsApp group. We will answer within the next 48 hours. Okay. That is about this one. We will share the notes right now. Okay. Here, right, the question is, the researcher wants to investigate whether smoking, alcohol use, and pesticide exposure are associated to development of Parkinson's disease. In this kind of question, right, in this kind of question, like this kind of question, so when you see that risk factors or the exposures and outcomes, when you see the word, when there's exposure, the answer either case control or the cohort, right? If you see any association between risk factor and outcome, most probably case control or cohort. It can be like analytical cross-sectional study or something like that, but generally case control cohort. Okay, give me 1 second. Okay, can you see the screen now? Okay, thank you very much. So I was discussing about this one. I hope you can hear as well, right? Okay. The thing is, if you hear the word about exposure and outcome of the risk factors, the design must be either case control or cohort. Rarely it can be analytical cross-sectional studies, but you need to know these things. Then see the nature of these studies. They are going to study the multiple risk factors like smoking, alcohol use, and pesticide exposure. If you need to study multiple, case control are good, because from the beginning you have cases, right? Patients and healthy. Then you can study multiple exposures. But when it comes to cohort, you can study exposure to multiple outcomes. But it takes time. Right? Okay, here you can see, now from the beginning of the study, 120 Parkinson's patients. From the beginning of the study, there are cases, and and 120 no Parkinson's. Those are cases and controls. Because of that, the answer is case control study. Cohort study begins with the exposures. Cross-sectional study. Cross-sectional study is to determine the prevalence. Case series and case reports are to describe the cases or the similar kind of cases. Okay, that is all about the study designs. We have shared several notes. I think nearly 6 or 7 notes we have compiled and shared. You can leisurely go through if you need more understanding. Okay. So we have few more MCQs, but I need to thank these people. So now they are right now in the department, and they are doing this for people, are doing a great support for me, and right now doing all these things, and this is not an effort. So I'm just here standing and talking to you. So if you are somewhere there, you must give a big round of applause, even though we cannot hear. So these are the people who are supporting me throughout the sessions. So we are sharing the videos, we are sharing the notes, we are preparing the notes, we have to do several things. Okay. Thank you very much. Okay, question number 10. I will give you 1 minute. Please go through this. This is very important. In this question, we are going to discuss about number needed to treat and absolute risk reduction, relative risk reduction, those things. Number needed to harm, those things. Okay, I hope you can hear, right? Okay. So this one, a randomized control trial. I will start this with the question. Randomized control trial evaluates a new statin drug for the primary prevention of cardiovascular events in a population of adults aged 45 to 60 years over 5 years. Right? Event rate in the placebo group is 10, right? Cardiovascular. So here we are giving for one group, we are giving statins. The group's control or placebo, another group. In statin group, the cardiovascular event is 6%, while the control group, 10% of them had cardiovascular events. And among the statin group, out of those who are used at statin, 4% developed muscle pain, while control group only 1% developed muscle pain. This is something that you need to understand. Then everything else is very, very easy. So I will explain this. Here, now, out of 100 statin group, 6 have developed cardiovascular events versus out of placebo, 100 people, 10 have developed the cardiovascular events. Now it's simple, right? Simple. What is the absolute risk reduction? Absolute risk reduction is, we have to get the common denominator. That is important. Out of 100, 10 have developed here and 6 have developed because of that. The absolute risk reduction is 4 per 100. That is the absolute risk reduction. Generally, out of 100 patients, right, 10 who are not using statins, 10 people will get cardiovascular events, right? And we can reduce that to 6 if we use statins. So the reduction is 4 out of 100. That is 4%. The absolute risk reduction is 4%. The next one is relative risk reduction. This is very important. Relative risk reduction is now yes. Out of those 10 who developed, right? 10 minus 6, that means 4 as a percentage. 4, the 4 out of 10 developed this disease because of not having statins. Because of that is 40%. Right? Out of those. It's simple. Out of the total people who got the disease, 40% could be reduced because of this one. That is relative risk reduction. The next important thing is number needed to treat. So number needed to treat is NNT. That is number needed to treat is here. Now, so we can get easy formula like 1 divided by absolute risk reduction or something like that. But the simple thing that I do is, now we are pretty clear that 10 minus 6. In order to recover 10 minus 6, right, we need to treat 100 patients, right? In order to get this benefit, we need to treat 100 patients. Then, in order to treat one patient, how many patients that we must treat? So that is 25. If we treat 25, right, then we can reduce 1K, right? So this is very important. So when it comes to vaccine trial, so I will give you one example. Okay, assume that out of 100,000 who receive vaccine, one will develop particular disease, while those who have not received the vaccine, 100,000, 2 will develop, right? What is the absolute risk reduction? Is 1 per 100,000, right? But the relative risk reduction is 1 out of T, that is 50%, right? You might see a newspaper article saying that, so if we give this vaccine, 50% of the cases can be reduced. But you can see the absolute risk reduction is very less. So the number needed to treat, right? In order to recover one, you need to treat 100,000 people. So in order to reduce one case, you need to treat 50,000 patients. Here the number needed to treat would be 50,000. Why? Why? In order to recover one, you need to treat. Sorry, the number needed to treat is 100,000. Yes. Right? If you treat 100,000 only, you can get additional one recovery. If the cost per vaccine is 5,000 rupees, yes, cost per vaccine is 5,000 rupees, right? So you can multiply this thing and see how much, as a country, how much we need to spend for the vaccine in order to recover one patient. So that is why we need to discuss about number needed to treat, absolute risk reduction. As medical professionals, we need to know the difference between relative risk reduction as well as absolute risk reduction. The answer, this here, the number needed to harm, which I'm not going to discuss, and I have prepared the note for the needed to treat. So we will share that one with you so you can understand more. So here, which of the following statements is most accurate? The absolute risk reduction for cardiovascular events is 10, which is not, I have discussed. The relative risk reduction is 40%, which I have discussed right now. We calculated it by 10 minus 6 divided by 10 into 100, that is 40%. Needed to treat to prevent cardiovascular 4, no, that is 25, it's wrong. The number needed to harm is 25, you can easily calculate that one, that is 33.3. Number needed to harm, because that is about this one, so you have 1% and 4%. So the number needed to harm, how are we going to calculate that one? So you need to get this additional benefit of 4 minus 1. In order to get the benefit of 4 minus 1, you need to treat 100 patients. You need to multiply that by 1. So the answer is 100 divided by 333.3. If the baseline risk of cardiovascular diseases were lower, the number needed treat would be expected to decrease. No. So if that is non-prevalent disease, very rare disease, right? Number needed to treat will be high, because if it's simple. Number needed to treat means the number of patients that we need to treat in order to recover one. In order to recover one, we need to treat many patients if the disease prevalence is less, or many people if the disease prevalence is less. Because of that, that is wrong. The answer here is B. Okay, let's go to the next question. Oh, here onwards, we will be having graphical visualization, especially. I'm not sure what are the exams, but I'm pretty sure that I did one class for the MD Part 2 medicine last year, right? Some of you might have participated in MD medicine Part 2. You will see these Kaplan-Meier curves, funnel plots, those things. Okay. Please go through this question, and we will share. We have prepared separate notes for Kaplan-Meier, funnel plots, everything. We will share those notes as well. I will give you 1 minute. Please go through this one, and we will discuss them. Okay, so let's discuss about the Kaplan-Meier curves. I hope you can hear. Right. A study compared recurrence-free survival between breast cancer patients receiving treatment A and treatment B over a 5-year period. The Kaplan-Meier survival curve show below summarizes the findings. So Kaplan-Meier curve is a visual illustration of survival, right? In the x-axis, you can see the time to recurrence. Here we are talking about breast cancer, right? Of two categories of treatments were received for two different people, and we are assessing the time, the recurrence rate over the time, right? And the y-axis is survival probability. So in the first year, both curves are overlapping, right? Once a patient develops disease, the survival probability goes down. So you can see it goes down. It's like this. And in addition, you need to know something called censoring. These are censoring. Censoring means we lost to follow-up, right? That means we don't know what has happened because this is survival. This is over 5-year period, right? Then the survival probability, how are we going to change? So denominator will be changed, right? Then if we have, so if we are following up 100 patients, if we cannot find one patient, then the denominator will change it as 99, right? So I have included that in the uh, short note as well, right? And this is going down, right? But you can see here the treatment A is relatively stable. They are not getting the survival probability is high at even 5. But if the treatment B, the survival probability is almost same up until 3 years. Then after 3 years, the survival of treatment B has gone down. So this is the treatment B is not effective. The recurrence rate is high, right? So this is what you need to know. But just by looking at this one, we cannot compare. In order to compare, there are several tests that we can use. The things like log rank test. Just the names are enough for the selection exams. Cox regression. And some other tests are there, which I have included in the note. Log rank test, Cox regression, those things. Okay. Right. We go to the question. Right now, here it's obvious treatment A is better than treatment B. Right. Treatment B shows better recurrences. False. Right. Both treatments show similar survival during first 3 years. Yes, that is correct. The tick marks indicate deaths among participants. No, it's not death, it's lost to follow up. These ticks are these things, right? Those are, we call them as censoring. Treatment A shows sharp decline in individuals around 3.2 years. No, treatment B shows sharp decline, right? And then the graph shows incidence rather than survival probability. No, the graph shows probability rather than incidence, the other way around. If we plot the incidence, the curve will be like this. And the other curve will be like this. It has to go up because with the case, the incidence graph would be the other way around of the Kaplan-Meier, right? It's wrong. Because of that, the answer is B. It's nothing but simple with regards to the survival. And when we compare, for example, now CKD, so we are comparing the dialysis versus conservative management, breast conservative management versus treatment, radiotherapy with neoadjuvant chemotherapy. So like that, we can compare in different ways. Okay. Question number 11 is discussed. Okay. Question number 12. That is very important, and many requests came with regard to forest plots. With regard to forest plots. If you have any questions, please put in the WhatsApp group. We are trying to answer within this period. If not, we will answer in the next 48 hours. These groups will be activated for some time, so you can discuss the things. Even there are groups which we have created for the previous sessions. Still, we are discussing the things in those groups. Okay, please take 2 minutes and see this one. This is about forest plots. Okay, forest plot. This is about the forest plot. Forest plot we use in meta-analysis. Right? These are two forest plots. Don't mistake, these are two different plots, right? So this is plot 1 and this is plot 2. I need to mention something specific. That's why I need to share. I need to include those two. So meta-analysis or the systematic review is something that you need to know, right? So let me share this one. So you need to know something about evidence-based medicine. In our practice, in our clinical practice, there are guidelines. Guidelines based on some sort of research evidence. If we can practice something with systematic review with meta-analysis, that is the best quality evidence. Best quality evidence. And the next level is systematic reviews without meta-analysis. Systematic review without meta-analysis. So that is the next level. If evidence comes from the randomized control trial, that is slightly less. Non-randomized experimental studies, less than that. Cohort studies, lower down. Case control studies, lower down. And cross-sectional studies and correlational are next. And if evidence are from case reports and case series, less quality evidence. And some diseases, there are no evidence at all, then the consultants decide based on their expert opinion. So that is the lowest level. Generally, this is put as level 5 or 6. Right? So in meta-analysis, assume that we have case control studies or treatment if case control studies. There are 5 studies conducted with regards to smoking and lung cancer. This study says the odds ratio is 3. This says the odds ratio is 3.5. This study says it has a protective factor. This might say 4. And this might say 0.1. Now, in order to put all these things into a guideline, now we are in a doubt whether to follow this research, this research, this research, this one or this one. Using forest plot, we analyze all these things together. We analyze all these things together using a forest plot, right? Coming here, right? So here there's something called pool. First one is about a cohort study, relative risk. This is about uh, stroke within 5 years, right? Whether the antihypertensives prevent, whether the antihypertensives prevent stroke, right? Okay. First study, the study says, right? So here the null value 1. I mentioned this null value 1, right? 1 means 1 times risk. Here we are going other way around. So now antihypertensives is a protective factor. Because of that, the relative risk are less than 1. So you can see study 1. Study 1 says somewhere here. It's about 0.7. They say that the relative risk is 0.7 in the study 1. That means there's 0.7 times risk of getting stroke if they are using antihypertensives. And importantly, these are the 95% confidence interval. 95% confidence interval does not cross the null value 1. So the 0.7 is significant. Study 2 has a result somewhere here. It's about maybe 0.9, but the 95% confidence interval crossed the null value 1. This study has non-significant result. But what about study 3? It has a small dot and it's about maybe 0.61 or 0.65 or something. 95% confidence interval does not cross the null value 1, right? And it's significant. So study 4, it says it's a risk factor. Those who are taking antihypertensives will get more strokes, but the 95% confidence interval cross the null value 1. Because of that, this is not this is not significant. And study 5 again says, right? It's a protective factor of 0.8 and 95% confidence interval is not crossing the null value 1. So if you analyze all these things, right? If you analyze all these things, and you can see predominantly there's a protective effect, but if you analyze together, you can see the pooled effect is here. According to this meta-analysis, we can confirm that the antihypertensives significantly protect the stroke incidence because the pooled effect is not crossing the null value 1. Right? Here it's a different study. Here it's a different study. It's a blood pressure reduction. Blood pressure reduction. So in blood pressure we reduce, right? There's no difference means 0. Okay, in blood pressure reduction we might have 2 groups, group A and group B. Okay, I will explain that in another slide. Okay, so group A and group B. Here the reduction may be 10 mercury millimeter. Here the reduction may be 10 mercury millimeter. We are comparing 2 groups. That means the difference is 0. So if we subtract one from the other one, in that case, right, the null value is 0. Simply odds ratios, relative risk, null value is 1. While when we are taking the difference, the null value is 0. The null value is 0. Right? Blood pressure reduction. You can see the study 1 says this antihypertensive significantly reduce the blood pressure. This one significantly reduce the blood pressure. This one significantly reduce the blood pressure. This one has not significant. This is not significant. And this one also significantly reduce the blood pressure. Right? I hope you are clear. And very importantly, the pooled effect also has significant reduction. Right? And important thing, another important thing here is you can see this 95% confidence interval is shorter. This is very short. That means this research might have large sample size or high quality, right? High quality research has shorter 95% confidence interval, while low quality research will have high 95% confidence intervals. You need to know. So also you need to consider this the size of this dot. If the size of the dot is very large, that means it's kind of high quality study. Right. So that's all about it. So let's go to the stems. A, in the stroke outcome, study 4 shows a statistically significant reduction. Here, the study 4 is not statistically significant because it crosses the null value 1. B, in the blood pressure outcome, study 4 shows a statistically significant result. No, it again crosses the null value 1. C, the pooled stroke results suggest increased stroke risk. No, it's less than 1 and significantly reduced. It has to be like this. If it significantly increased, it should be the more than the null value, right? So it is wrong. This is correct. Dash vertical line represent the pooled estimate. Yes. Sorry. The dashed vertical line represent the pooled estimate. No. So this is also wrong. There's a problem in this MCQ, right? Dash vertical line represent. This is wrong. Represent the null value. Okay. E, larger line indicates statistical significance. No, statistical significance indicates if this 95% confidence interval is not crossing the null value, right? So that indicates statistical significance. So this does not indicate. So because of that, I'm sorry, there's no correct answer. Okay. So there must be some problem here. But anyway, so this is, I hope you understood the forest plot well. All stems are wrong. Okay. Now forest plot. Sorry, funnel plot, which is another important aspect. We will discuss. Take 2 minutes and go through this one. Okay, before talking about this one, I need to discuss a little bit about the funnel plot. Here's the funnel spot. This is a funnel spot, right? In this funnel spot, this is also there are several things that we can say. In the meta-analysis, I told you in meta-analysis, we are analyzing different studies together. In the funnel plot, I told, so the now y-axis is standard error. The minimal standard error that you can have is 0. That is somewhere here, right? Small standard error means standard error less means high quality studies. That means narrow 95% confidence intervals. Right? Narrow 95% confidence interval. In a funnel plot, right? This lines indicates the 95% confidence interval. Since the 95% confidence intervals are lower, the high quality studies or the large scale studies are there. Large scale studies are there and top, small studies are there at the bottom. The red color ones are the small studies, right? If you assess everything together, the mean effect size is here. Here we are talking about mean difference. We are talking about the reduction of HbA1c. There are several studies conducted to assess the reduction of HbA1c because of the lifestyle intervention. So here it says that it's 0.2. It's reduced, but we see the effect. So for this one, you need to understand a little bit more about the funnel flow. So I have included this in the text as well. We will share the short note with you also. So the first one, you can see the pool effect is mean reduction of HbA1c is 0.5. You can see the large studies are equally distributed in either side, right? The small studies are equal. So that means there's no publication bias. Symmetrical studies are, if the studies are symmetrical, that means the good results as well as bad results are equally published. So we can rely now after analyzing all the studies, we might say that there's an effect, but the reason might be no effect studies are not published. That is what we are assessing here. But here you can see, right, the mean effect is 0.5, right? You can see the large scale studies are there symmetrical. As the large scale studies are symmetrical, there's no problem, but you can see the small scale studies they are in the one side. That means small scale studies which shows non-significant results or this side results are not published because they are small. If you think about the large scale studies are well funded, people are publishing, experienced researchers. So whether they had positive result or negative result, they published it. But if you look at the small studies, they tend to unpublish if the result is not positive. So this indicates publication bias. And here, you can see the large studies are asymmetrical, while small studies are distributed here. Large studies are asymmetrical. That means high quality studies give different results. Very good result says that metformin is effective. Another very good study says that metformin is not effective, right? That indicates there may be actual problem, but this may be the methodological issues or area-wise difference or data quality problems. There can be many reasons because the large quality studies are generally good, but population variations can have these differences. You can see this one I am not going to explain because I have included them here, including heterogeneity. So very wide evidence. Some studies say extremely good, while some says extremely bad. Here also you can see outliers. This indicates outliers. You can leisurely go through this one. We go to the question. A meta-analysis of pooled results from 20 randomized control trials is the effect of lifestyle intervention on HbA1c reduction in patients with type 2 diabetes. In the funnel plot, blue points represent large studies. These are included in the exam. This part will not be included, but since this is a MCQ class, I included all these things. Which of the following statements best describe? Right? The plot suggests possible asymmetry. Here you can see the large studies are symmetrical while most of the small studies are only in one side. This indicates possible asymmetry because small studies are more unevenly distributed around the fold effect, right? So in the exam, you will not get this kind of big stems, but I included this intentionally because for your understanding. Then not blue points are expected near the bottom. No, the blue points are expected at top because they are high quality studies. This is wrong. The dashed vertical line represents standard error of fold estimate. No, dash one is the fold effect. So it is wrong. Studies outside the funnel are statistically invalid. No, we cannot say that these are invalid, but there must be problem either as methodology or something like that. And a symmetrical funnel plot completely rules out publication bias. That is also not the funnel plot itself. We cannot say about the publication bias. Okay. I hope you understood, and we have shared the funnel plot note as well with you. So please leisurely go through. So we have two more MCQs with both that one. Next one is ROC curve, which is very interesting one. And somebody asked about sensitivity, specificity. We will discuss these things. I will give you 2 minutes. Please go through the MCQ and we will discuss. Okay, I hope you can hear. We go to the slide. Okay, so this is screening test. We have prepared another note for screening as well. We will share this one. So here we have disease present, disease absent, test positive. In screening, right? We are talking about whether we can use a simple test to screen the people. Either it's because of easier to apply, less cost, and we may need more expertise to apply diabetes, more expertise to apply the diagnostic test. So like that. So screening test. In order to say whether a screening test is good or bad, right? There are a few things that you need to understand. Those are sensitivity. Sensitivity is ability of screening test to identify positives as positive. That is, out of total diseased patients, out of 200 patients here, how many of them have identified? So this side we have screening tests. This side we have the gold standard test. Out of 200 patients, 180 are identified. 180 are identified. So the 100 sensitivity is 90%. That means if you are given 100 patients, the screening test will identify 90% of the patients. Right? Specificity is the ability of screening test to identify negatives as negatives. Out of 800 negative patients, 680 of them have been identified as negatives. This percentage, I think it's at 85. The calculation is wrong, please let me know. The next one is, out of the positive results, how many of them are actually having disease? That is what is called positive predictive value. Positive predictive value. Out of 300 positives, right? 120, sorry, 180 are identified as diseased. That is roughly, yeah, 60%. Positive predictive value is low. And keep in mind, there are no cutoffs for this. And the last one is negative predictive value. Negative predictive value is out of total negative results, that is out of 700, 680 of them have identified as negatives. 100, I think that is about 97.1%. Right? In clinical medicine, if you see a ST elevation in a patient, right? Can you think a while? What is the most important property of the ECG that you need to know in clinical practice? You find ST elevation, right? You find ST elevation. Not the sensitivity and specificity. Positive predictive value is important because the positive predictive value says if the test is positive, what is the probability of having the disease? If the ST elevation is there, what is the probability of having a proper myocardial infarction? So in clinical practice, we are generally using positive and negative predictive value, especially individual patient care. When it comes to population screening and population level, sensitivity and specificity are important. And the other most important thing is with the disease prevalence, specificity and sensitivity will not change with the disease prevalence, while positive predictive value and negative predictive value will change with the disease prevalence. If you go to Candy and if you try to find out in Candy, if you try to find out CKD patient, right? As CKD prevalence is less, the positive predictive value will go down. If you get a positive test in Candy, and if you get a positive test for CKD in Anuradhapura, you will have a higher positive predictive value in Anuradhapura because the prevalence is high, right? I have included these things in the short note. Now we have shared that one. You can refer it. And there's one more important thing, that is likelihood ratios, right? Likelihood ratios, there's a positive likelihood ratio, that is likelihood ratio positive, included here, that is sensitivity divided by 1 minus specificity. Sensitivity means true positives. Out of the disease, how many of them have identified as positives? And 1 minus specificity is the negative probability of identifying the negatives as negatives. 1 minus specificity means identifying negatives as positives, that is false positives. True positives divided by false positives, right? Sensitivity divided by 1 minus specificity, that is 0.9 divided by 1 minus 0.85, right? The answer is 6. That means if we get a positive result, right? So like, right? So being a breast, if this is related to cancer, right? We have like 6 times probability of having him being a breast cancer patient, right? So this one. So I described this in the note. And negative predictive value. So likelihood ratio. Sorry. So I was talking about the likelihood ratio positives, and negative likelihood ratio is 1 minus sensitivity right, divided by specificity. In other way around, false negatives divided by true negatives. Here you will see the answer is around, I think, it's displayed here. It's 0.12. You apply. So the negative likelihood ratio of a screening test should be as less as possible, while positive likelihood ratio should be as high as possible. Right? So you can go through. So you need to know the likelihood ratios as well. And one important thing is, so now I'm coming back to the ROC curves, right? In ROC curve, we plot sensitivity here and or the true positives here, and 1 minus specificity here or the false positives. Okay, we need to find out infections, and our diagnostic test is CRP. Right? Generally, we take the cutoff as 5. Assume that we took cutoff to 200. If we call it as positive, if the CRP level is 200, right? CRP level is 200. So we call 200. So everybody who's having a CRP value more than 200, everybody who's having CRP value more than 200 will be definitely positives, right? So if our cutoff is 200, true positives will be high because everybody is having a disease. True positives. So when you reduce the cutoff from 200 to 1, right? Still you will detect false positive rate. This side false positives, false positive rate will not go up, but slightly will go up. Slightly it will shift like this, right? But the true positives will go up. But at certain point, when it comes down from 5, suddenly true positives will not increase while the false positives will increase. Right? A good diagnostic test, if you understand this, the good diagnostic test, a good diagnostic test should have a shape like this. True positives should go up, and at certain point, the false positive should go up. So the reference line is something like this. If something is going in this line in ROC curve, that test is not good. While if something is like this, that test is good. Right? If a line like this, we call something called area under the curve is 0.5 because it's half. While if something is like this, the area under the curve is 1. Right. We go back to the question. Here you can see 3 tests. Test A has good area under the curve of 0.97. Test this is 0.97, and the next one is 0.86. This one has 0.66. As this is more closer to the reference line, this is the worst one, this is middle one, and this is the best diagnostic test. Right? Okay, so study evaluated 3 diagnostic tests, test A, B, and C for detecting diabetes retinopathy in patients with type 2 diabetes. The ROC curves and corresponding area under the curves are shown. Right? Okay, which of the following is the most accurate? Test C has the best discriminatory ability. No. The diagonal reference line represent perfect. No. This represent the worst one. Test A shows the best overall diagnostic performance, which is correct. Test B has lower sensitivity than test C, which is wrong. The area under the curve 0.5 indicates excellent. No. 1 indicates the excellent one. So in area under the curve, simply you need to know if something is like this, that is the best one. And another thing is in other way around, if something is like this, what do you think? Again, that is good, right? It should not be to this side, or either for this side, either for this side, or in this side. Anyway, it has to be like a corner of 90 degrees angle, something is like this, we call this as a good test. That is all about the ROC curves. And we move on to the final question for today. I have covered almost all the aspects through MCQs and through short notes. Right. Okay. Please take 2 minutes and read this one. Okay, the final questions. I have received many questions through WhatsApp, and I have answered many of the questions through this discussion. Then I have answered several questions during this discussion, and the rest of the questions we answer to the WhatsApp group as soon as possible. So we received private messages plus common messages. So we'll answer almost all the questions as soon as possible in the next 2 to 3 days. Right? The final question, so read it one. This one, researchers studied the relationship between daily exercise duration and resting heart rate. Right? Scatter plot showed that. So I'm sorry that the shared document does not have this graph. Right? So now you can see the graph. You can see when you increase the exercise daily exercise duration, the resting heart rate goes down. The resting heart rate. Sorry. Okay, the resting heart rate goes down, right? The resting heart rate goes down. The resting heart rate goes down, right? So the R equals minus 8 to 82, right? I will explain this first one. So when you have this kind of scenario, X and Y plot, when you plot this one, so what you do is, okay, so here it's exercise duration. Here the resting heart rate. Right? You need to plot these things like you did in your O-levels. And you get the common line like this, right? So the statistic that we use is R. We call this as correlation coefficient. Correlation coefficient, right? If you get something like this, the dots like this, right? It's a perfect line. It's a perfect line. So in that case, the R, the maximum value R can have is +1. We call that perfect positive correlation. Anything below that, something like this, will range from 0 to 1. If there's no association, right? So there's no association, the R will be 0, while if it creates a perfect negative relationship, the R will be -1. So R, correlation coefficient, R value varies from -1 to +1. Here the R equals -8, 0.882. That negative correlation, right? Negative correlation, right? Here it's a negative correlation. Let's go. The variables show weak negative association. We don't know whether it's weak. There are classifications like 0.5 to 0.7 weak for numbers. This may be correct. Weak or strong. There's a negative correlation. We are not sure about weak. The variables show a strong positive correlation. No, this is a negative correlation. The value of R proves that exercise reduces resting heart rate. This is about clinical significance, right? There's a statistical significant association, but we cannot say that exercise reduces. In this sample, it's there, right? The actual significance, we need so many other criteria like that we discuss under causation, the things like temporal association, coherence, specificity, those things, right? So we will share the causation note as well. Then you will understand the difference between the clinical significance as well as statistical significance. Please, I will share the causation note. Okay, so this is wrong because they are talking about the clinical significance. The correlation coefficient ranges from 0 to 1, no, it ranges from -1 to +1. And the variables show a strong negative linear relationship. Generally, when you have obvious shape like this, it is strong. Rather than that, the most important part is the linear association. In correlation coefficient, we can only identify the linear relationships. Sometimes we can have things like this, right? This kind of associations. The things like, right? In correlation coefficient, it might assume like this, and R might be equal to 0. But this one is a different association. So to function this, there are formulas like ax squared plus bx plus c. If you can remember your O-level maths, right? We learn these things, right? So these are different. So these kind of curvilinear or this kind of different relationships cannot be identified through correlation coefficient. Because of that, the best answer is this one because of this linear relationship. That ends this one, and I promise you to, so I have some messages as well. So this ends the session, and I promise you that I will answer all these questions within the next 2 to 3 days, because we have, and I couldn't share all the short notes, and I'm compiling all these short notes in these books. I'm writing these books right now, which will be published very soon. One is about short notes on statistics and research methods. We will share all these information through the groups. So this is the short note book and MCQs on statistics and research methods. So this is very large book. So I have included almost all the MCQs in that book. We will share that book very soon. And yes, that is about it. And final message, Anuradhapura Medical Association, they are conducting several classes related to postgraduate exams. Please go to the website, Facebook group, and please go to Facebook and like it, because so they are conducting several classes. So thank you very much for participating. I think we did nearly 3 hours. I hope I covered almost, at least introduced almost all the concepts, and there are some other concepts. If there are some other concepts, I would like to answer through WhatsApp or through emails. So please post your questions in the group. We will answer those things. Okay, thank you very much for staying, and have a good night. And now you can have your dinner. So I didn't stop for the dinner. Thank you very much. So now we also received our dinner. Thank you very much for coming, and I wish you all the best to pass the examinations. This is the first time that we deal with more than 1,000 individuals. This is the first time. And even at the latter part, I think now we are having nearly 500 participants with us. So thank you very much. So we will close our session. Thank you very much and good night.